Hi.
Hi. Hello, everybody.
Hi, welcome everybody to the Laws of Nature series. This is a series organized by Paula Reichert, Dirk Deckert of the LMU, Angelo Bassi of the University of Trieste, and myself of the KU Leuven in Belgium. And this is a series to promote mathematical, physical, and philosophical ideas in the field of foundations of physics. And this is the autumn series. Okay, we already had 3 sessions, and today's sessions is going to be about typicality, probability, and physics. So with Barry Loewer and Dustin Lazarovici, okay, with a more philosophical take on things. Okay, Paula Reichert will be chairing this session, so I'll hand the floor to her.
So welcome also from my side, and thank you for coming. So we have 2 talks today. First Barry Loewer and then Dustin Lazarovici. And let me just remind you that we would like to have during the talk just questions in the chat if you really have one, and postpone other questions to after the talk. So we have about 45 minutes talk and 15 minutes question after each talk. And then in the end, we have another 1-hour general discussion where you can ask questions to both speakers. So we start with Barry Loewer. So I'm very happy that you are here. Barry Loewer is professor for philosophy at Rutgers University, and he's well known for various different works in various fields of philosophy, maybe best known for his work on causation and scientific laws. And today he will speak about probability and typicality, friends or foes. So thank you, please.
Okay, thanks, Paul. Oh, go ahead.
Maybe you can switch to the full screen mode again. I think somehow it went back to the working.
Not by me, I didn't do anything. What do I have to do?
So if you just click on slideshow in the middle of the menu,
Yeah.
And then let me see. Yeah, resume slideshow. Yes, perfect.
Yeah, that's
thanks,
okay.
Barry. All right.
Okay.
Okay, so thanks, Paula. Thanks, Ward and Dirk and Angelo and all for inviting me to do this. It got me to think about something that I've been meaning to want to think about, and also to invent a new word, as you'll see in a while. So I want to investigate to what extent typicality and probability are friends or their foes. Advocates of both are friends, I assure you at the beginning. So Dustin and I are friends. So typicality and probability approaches to statistical mechanics are often thought of as radically different and competing. So what I want to do is to describe an approach to laws and probabilities that's based on David Lewis's best system, Humean account of probability, that I call the Mentaculus, and a typicality approach based on work by Shelley Goldstein and Dustin Lazarovici and Mario Hubert and various other people, which I provisionally will call here's my new word, the Tipitaculus. Okay, I have some trepidation to use it because the advocates of this may find it objectionable. If such, you're going to have to suffer through it for a while, but you can chide me later about it or tell me not to use it. Okay, and my argument is going to be that while there are some important differences between them, they're more similar than they may appear initially. But behind the debate between typicality and probability, at least as applied in the context of its Mentaculus and Tipitaculus, is a more fundamental metaphysical debate, I think, over the nature of laws and physical probabilities between Humeans and anti-Humeans. You're probably familiar with this debate because you've been talking about laws of nature, but maybe it wouldn't hurt to rehearse a little bit of what's involved in it. So there are primarily two accounts of the metaphysics of laws and physical probabilities in the philosophy literature. One I'll call, one anti-Humean account I'll call a governing account. According to it, laws have fundamental features of reality that are over and above the distribution of events, and laws govern the distribution of events. Advocates of views like this are Tim Maudlin and a different version by David Armstrong and Michael Tooley, older versions. Basically, they go back to the idea that laws make things happen. They take the state of the world at a time and produce the state at subsequent times. And there's a view about physical probabilities that goes along with this anti-Humean view that says that physical probabilities are fundamental features of reality too, that play a role in governing. They measure the degree to which an event produces subsequent events, usually by way of law. And views of probability like this fit in with what are often called propensity or single case propensity views about probability. We go back to Popper and Geary and various other people hold views like this. In contrast to Humean views reject the idea that laws govern or produce anything, or anything over and above the distribution of events, but rather laws describe patterns among the distribution of events in ways that are informative, simple, and satisfy other criteria developed during the history of science. And the two accounts, I should also mention that we won't really get into this here, at least I won't, unless it comes up in questions. They go along with different views about the nature of time, the direction of time, and about the nature of explanation by law, and different views about causation and counterfactuals. Okay, so here's David Lewis's Humean account. I'm not sure who's in the audience, but there may be, all philosophers know this pretty much, but there may be some physicists who aren't familiar with what's gone on in philosophy in this debate recently. So on David Lewis is the usually cited as the person who sort of revived a kind of Humean view and gave it a particular formulation. So he had a certain view about the ontology of the universe. You don't actually have to hold the details of his view to have a view about laws similar to his, but let me just say I have a picture in mind, say something about his views about ontology. So he thinks of the world as there being a universe, there being something like a space-time arena, which has some sort of metrical structure, and it's filled up with the instantiation in regions or at points in the space-time of fundamental properties that he calls perfectly natural properties. On Lewis's view, these properties are what he calls categorical. And that means that their instantiations are nomologically independent. By their very nature, they're nomologically independent of the instantiation of properties in distinct regions. He calls this the whole distribution of events in the space-time arena the Humean mosaic. Like I said, there are modifications of this that don't hold some of the views which I think are not in tune with contemporary physics. So one can make modifications in this, but I won't get into that here. Okay, this view about laws is that laws and other nomological items like counterfactuals, probabilities, causation, and so on, supervene on the Humean mosaic. So fundamental laws, in Lewis's view, are not ontologically fundamental. They don't govern, though they still might be laws that we might call nomologically fundamental. So the laws of physics are nomologically fundamental, but they're not metaphysically fundamental. And Lewis is famous for proposing accounts of other nomological modalities, probabilities, counterfactuals, causal relations, and so on, in terms of laws and other aspects of the Humean mosaic. We'll get into a little bit more what he says about probability in a minute. Okay, so here's his statement of his account of laws. He says, take all the candidate deductive systems whose theorems are true. Some are simpler and better systematized than others. Some are stronger and more informative than others. These virtues compete. An uninformative system can be very simple. An unsystematized compendium of miscellaneous information can be very informative. The best system, the best of all of these, there may be more than one that count as best, is the one that strikes as good a balance as truth will allow between simplicity and strength. How good a balance that is will depend on how kind nature is. And Lewis says that a regularity is a law if it's a system of the best, if it's a theorem of the best system. I think that last remark needs some refinement because we won't call every theorem a law, and there might be some things we want to call laws which we wouldn't call regularities. But this is Lewis's statement. And I would add to it that there might be other criteria that candidates for best system aim to satisfy. One of them we'll talk about is fit. Another one is mathematical tractability, or there being symmetries in the system might be something important that we want a system to satisfy. That it works so that the universe has subsystems to which the laws apply or approximately apply might be another criteria. Okay, here's how probabilities are introduced into Lewis's account. Can I just make a remark? This construction next to me, is that interfering with this?
I think it's
in Manhattan, and unfortunately in Manhattan, they're building all the time.
But it's only minor. I think
Okay, I
okay.
apologize. Or Manhattan apologizes. But,
No problem.
okay, so probability is introduced into the language in which candidates for best system is formulated, not as a name for some particular fundamental feature of reality, like propensity theories usually consider probabilities to be, but rather probability is introduced as a device for providing information, additional information at a small cost and simplicity. Here's a very simple kind of illustration of that. Think about a long sequence of the outcomes of coin tosses and think about trying to describe it. Well, to describe it in detail would take, a long time, but it can be described fairly simply and informatively by saying that it's the outcome of coin flipping, of which the probability of heads is a half, and the flips are independent. Lewis then says that when you introduce probabilities into the axioms of the best system, you measure the fit, which is like a kind of informativeness of the system, or the strength of the system, by how likely the history how likely the fundamental history of the world is, or the macroscopic history of the world, that's my addition, or some test propositions are given the system. Okay, so this needs some more attention and fixing up to really characterize fit precisely. And that could come up in questions. Okay, Lewis thought that his account of probability applied only to dynamical laws that specify the probabilities that one state is followed by alternative states, like on propensity accounts. This has the consequence that if determinism is true, then all physical probabilities will be either 1 or 0. But this is wrong. Lewis's very account of probability allows for there to be probabilities that are compatible with deterministic dynamics. Okay, the reason is that it allows for there to have a probability distribution over the initial conditions of the universe, or over the possible the trajectories that conform to the dynamical laws of the universe. And this is compatible with there being deterministic laws. Okay, so here's how probabilities provide information about the world. If the best system of the world entails that the conditional probability of B on A is some value X, then it provides information by advising that the laws say that one's conditional degree of belief in B given A and the system should be equal to X. And this is a version of what Lewis calls his principal principle, which he thinks is really what gives how we understand the notion of probability. We understand the notion of objective probability as kind of like an ideal advisor of what our degrees of belief should be. I put it in the form of advising about conditional probabilities because it's going to be important to the way I want to understand it in my discussion of the Mentaculus. Okay, so now let me tell you what the Mentaculus is. Okay, so it's a theory of the world. It's supposed to be a theory of everything, in a way. And of course, I don't know what the ontology of the ultimate theory of everything is, if there is one, because nobody knows what it is. And I don't know what its dynamical laws and other laws are going to be like, because nobody knows what they are. But I'm supposing that there is such a system, the universe. But in addition, the Mentaculus has two other axioms. One is something that was introduced by my friend David Albert in his book Time and Chance, that he calls the past hypothesis, that I'm sure you're all familiar with. And that's a characterization of the macroscopic state of the very early universe, the thermodynamic state of the very early universe, with the assumption that its entropy is very, very, very small. Okay, there are issues about exactly what the past hypothesis says and whether it even makes sense to talk about entropy in the very early universe, but that's not something I'm going to get into. The other axiom in the Mentaculus is called SP, that stands for statistical postulate, and it's an objective probability density specified by the Louisville measure over the possible microstates that realize this low entropy early macro state of the universe. And it basically says, or has the consequence, that the entropy increasing initial conditions are overwhelmingly probable. Okay, of course, that needs detailed argumentation, but that's why we pay people in statistical mechanics to do that. The big question about the Mentaculus. Oh, I should say, where does this bizarre word Mentaculus comes from? Probably a lot of people here know, but let me just stop to say something about it. So there's a film some of you may have seen called A Serious Man. That's by Ethan and Joel Cohen. It's a really interesting, good film. If some of you are physicists, it's about a physicist having a sort of a midlife crisis. So you might want to see it for that reason if you haven't seen it before. But at any rate, there's a minor character in the film who is clearly out of his mind, and he's scribbling in a book, and somebody asks him what the book is, and he says it's the Mentaculus. Then they ask, what's that? And he says, it's a probability map of the universe. Okay, so David and I took this as a term for this account, perfectly aware that it's taken from somebody who used it, who was out of his mind. Okay. I've had the problem in the past that when I do something that's meant to be self-irony, people think that they're telling me about it, but I know perfectly well why I chose the word. That's because it is very ambitious, and we think it has lots of incredibly interesting consequences for our universe. I'll say a little bit about some of them, if it were true. Okay, so the Humean Mentaculus says that the Mentaculus is the best system, in Lewis's sense, of the universe. And the past hypothesis and statistical postulate are laws because they're components of the best system. And probabilities within the system are understood as probabilities are on the Humean account. Okay, so here's my new word now, the Typicality. It looks just like the Mentaculus. Okay, it's a theory of the universe, except 3 is replaced by what I call TP, and that's a typicality measure, also specified by the Louisville measure, over conditions compatible with the early state of the universe. And it says that these are typical. And it has the consequence that entropy increasing initial conditions of the universe are typical ones. Now I need to explain a little bit about what typicality is, and I'll do that in a moment. So the Mentaculus and the Typicality seem very similar, and both employ the Louisville measure, but understand it very differently in the two ways I just described. And I'll say right off that both are literally compatible with Humean and anti-Humean metaphysics, but the Mentaculus fits much better with Humeanism, and the Typicality fits much better with anti-Humeanism. That's one of the themes of this talk, and I really want to see if I get some response from people here about that. What do you think about that? Okay, first question is, what is typicality? Okay, so here's the characterization of it that one sees around. There's a nice paper about this by a recent Rutgers PhD named Isaac Wilhelm I'm going to look at. But here's my quick characterization. To say that a property F is typical among members of some set S, if S has a lot of members and all or almost all of them are F. So typicality concerns the relative size of the set of F's and S. It's not a probability notion. That's the important thing. It doesn't involve F's being randomly selected from S. Because of this, the Typicality avoids the problem of explaining what statistical mechanical probabilities are. Because that's a problem that the Mentaculus faces. What are statistical mechanical probabilities? How to interpret them in statistical mechanics? That's a problem that was there from the very beginning with Maxwell and Boltzmann. Are they epistemic? Are they frequencies? What? Okay. Well, the Lewis account, the Mentaculus, has a view about what they are. But that's not a problem that the Typicality faces because it doesn't have this probability notion in its fundamental formulation. Okay. Although typicality is not probability, F's being typical in S is claimed to justify inferring that X is F on the basis of its being in S, just that learning that S's are probably F justifies inferring that a randomly selected S is F, or justifies having a high degree of belief that it's F. Also, typicality is supposed to justify there being no need to explain why X is F. One knows that X is in S. Okay, let's get to thermodynamics briefly. I assume, I'm not going to say very much about it, except that's what these both accounts are supposed to be accounts of thermodynamics. So thermodynamics is the science that concerns regularities involving certain macroscopic quantities, including pressure, temperature, total energy, average frequency of radiation, and so on, and entropy. And thermodynamic quantities are ubiquitous and can be characterized for all forms of matter and fields. Okay. We might think about a kind of thermodynamic characterization of the world. Instead of Lewis's Humean mosaic, we might think about the thermodynamic mosaic of the world. That would be like dividing the universe up into small regions, space-time regions of regions, and say what the thermodynamic quantities are in these small space-time regions. I think that if we knew, or if we had a big list of what if we knew the thermodynamic mosaic of the universe, we could use that to determine a lot of other properties about the universe. Where my cat usually comes down when I'm here teaching on Zoom. It's not here right now, but when I'm down here, I'm often talking about Schrodinger's cat, so my cat likes to come down and listen to that. And I'm bringing him up because I'm imagining that if I had the thermodynamic description of my room, you could know where the cat is, because he's a little bit warmer than the other things in the room. A little bit, his density is a little bit different, and so on. Okay. Okay, both the Mentaculus and the Typicality provide explanations of thermodynamic regularities. They're a bit different because the Mentaculus explains by entailing probabilistic versions of thermodynamic regularities. Okay, the regularities I have in mind are chief among them the second law of thermodynamics, but also all the other thermodynamic regularities that would say when the thermodynamic system in a certain region is like this, and the system's isolated, then it'll be like this at some other time. The Typicalus explains by entailing that satisfaction of thermodynamic regularities is typical. So they provide somewhat different kinds of explanations. Okay, there are two big differences that I want to keep in mind, and maybe we'll discuss more later, between the Mentaculus and the Typicalus. One is that the statistical postulate is a contingent law. So the way it's handled in the Humean best system is it's contingent because it depends on the structure of the Humean mosaic. Different Humean mosaics will have different laws. Okay, the I don't know what to call it. The typicality postulate, TP, is closer to an a priori principle that characterizes the meaning of most. Now, there's an issue about why we're characterizing the meaning of most using the Louisville measure, because we can't just use a numerical notion of most when dealing with a continuous infinity of initial conditions, as we are. Advocates of the Typicalus have things to say about that. It's the measure that fits nicely. It's stationary and has other features, fits with the dynamics. Okay, the other difference is that the Mentaculus employs what I call the principal principle, or the new principle, to make inferences involving degrees of belief. So it makes inferences from the conditional probability of this given that is such and such to what your conditional degree of belief should be. While the Typicalus employs a principle that's similar to what's come to be called, or Cournot's principle, which says that from F's being typical among S's, one should infer that S is an F. Okay, so so like I said before, the reason we chose this name Mentaculus is that the character in the Coen Brothers film describes his book as a probability map of the universe, and that's what the Mentaculus is. And the reason it is because it assigns it as a probability density of all the physically possible initial conditions of the universe. That will entail conditional probabilities for all physically specifiable propositions that have conditional probabilities over for all pairs of such physically specifiable propositions. And David and I have argued in various places that these conditional probabilities are the basis for counts of the second law of thermodynamics and other thermodynamic laws, I was saying before, and for the other temporal asymmetries, like the fact that we have a different epistemic relation to the past and the future, and we have different, influence the future to an extent, but we can't influence the past in any way that's interesting to us. And also, I think it provides the basis for special science laws and for counterfactuals and for causal relations. In its way, it could be looked at as promising to realize Oppenheimer and Putnam's dream of unifying all of science. So that's why we're using the term Mentaculus, because this very ambitious claim clearly indicates we're out of our minds. Okay, here's a picture now of what the universe looks like on the Mentaculus. Okay, the cylinders are supposed to be macroscopic histories of the universe, while the thin lines are microscopic histories of the universe, detailing the exact microscopic state. Let's say we're just dealing with classical mechanics, the positions and momenta of all the particles in the universe. Let's suppose the universe is finite to keep this in spatial and temporal extent to avoid certain worries we could get into then. Okay, so the thin lines are all straight and they never merge or separate branch. That's because the fundamental dynamics we're assuming is deterministic. Okay, but the cylinders do branch, and sometimes there's even merging in that different microscopic states and even different macroscopic states might merge into a macroscopic state. But as the entropy of the universe gets bigger and bigger and bigger, in accordance with the second law, since higher entropy macroscopic states take up much more of the phase space, they will get bigger and bigger and bigger. And so while this branching is pretty typical, I could say, in the early part of the universe, as the universe gets older and older, and entropy gets bigger and bigger, there'll be more and more this merging. Okay, so I want to start comparing and then introducing some criticisms of the Mentaculus from the side of the Typicality. While the Mentaculus and Typicality agree with respect to thermodynamics laws, the Typicality seems to say nothing about propositions whose measure is not near 1 or 0. Although the Louisville measure assigns values to arbitrary propositions, unless this value is 0 or very near 0 or 1 or very near 1, this merely serves to classify them as typical or atypical. In almost all cases, this involves types of events, that's to say, where they're, and I didn't write this out right, if the values aren't 1 or 0, there'll only be 1 or 0 for events which are repeated many, many times, or at least are repeatable. For propositions that describe events that occur just once, and here's an example I've taken from a paper by Dustin, that the President of the United States elected in 2028 is female, the Typicality seems to say nothing, since the measure of the set of conditions that realize this proposition is presumably not near 1 or 0. Well, it might be very near 0 if we're just talking about literally that proposition. I guess of all of the initial conditions of the universe, very, very few of them have even there being an Earth there, let alone a president being elected. So that would be very atypical. But if you think about conditional probabilities, the probability of there being a female president elected in 2028, given what we know now about the macroscopic condition of the Earth, presumably that's something that's in between 1 or 0. But the Typicality will only say whether or not it's typical or not typical, so it won't say anything about that. Okay. So this contrasts with the Mentaculus, which assigns probabilities to this proposition and the corresponding conditional probability that I mentioned, and to many other propositions that involve events that occur only once or a few times. However, the Typicality can introduce frequency probabilities. There's a nice paper about this by Mario Hubert. It's also mentioned by Dustin in a paper of his and various other people. So here's a brief description. While the Typicality accounts for thermodynamics in terms of typicality rather than probability, it needn't reject objective probability, but it does support a frequency account that is applicable to thermodynamical properties and to other systems and to other properties and systems. The idea is that there are recurrent situations that typically, according to the measure, result in stable frequencies that exhibit features of randomness in the sense that frequencies are not describable by simple rule or not compressible. For example, tossing a coin under usual conditions 100 times typically results in random appearing sequences with between 48 and 52 heads. And the idea is that the initial conditions of the universe are such that, given the other macroscopic conditions that are required for them to even make sense of tossing coins and so on, and a description of the coin and the tossing and so on, that the tossings will result, tossing it 100 times will typically result in there being between 48 and 52 heads. And the Typicalus can explain this by citing the fact that it's typical on the initial conditions of the universe. A flipped coin will result in under such circumstances, will result in such sequences. Okay, let's come to criticisms that are made of the Mentaculus. Okay, I've taken these criticisms from these two papers I mentioned, one by Dustin and the other by Mario. Okay, but I've heard them from other people too in various forms, but they have nice formulations of it. The main thing is they look at the Mentaculus and say, you guys are out of your mind. Do you really think that there's an objective physical probability to there being a woman being elected president in the United States in 2028? Even an objective physical probability, conditional probability of a woman being elected president of the United States, given the macroscopic description of given the description of the macroscopic facts that we know about the United States and the Earth and the universe now. Okay, that seems rather a strange or a vicious thing to say. Okay, I don't know what people's response to this is. Of course, there have been some people who think that there really are such objective probabilities. So-called objective Bayesians will sometimes attribute objective probabilities to all sorts of statements. But in the objective Bayesian literature tradition, these usually come from somehow rules of reasoning, or they're a priori in some way. That isn't the way the Mentaculus is introducing these objective probabilities. They are objective probabilities because they are features of the patterns of events in the universe. Okay. They're contingent. Okay. All right. So one objection is that why believe that there are all of these objective physical probabilities? I mean, even if the Mentaculus got thermodynamics right, why would that lead you to think that to extend the probability distribution to other things like women being elected president of the US and so on? So that's one kind of objection. And the way the objection sometimes goes, make it a little more precise, is to say, look, there are many probability distributions which will agree with the Louisville distribution in getting thermodynamics right. At first sight, it looks like any probability distribution that is continuous with the Louisville distribution, isn't too different from it, is continuous with it, will agree with respect to thermodynamics. But these might disagree, these are the other distributions, with respect to other things, like particular events, like women being elected president in the year 2028. And that seems right at first. So the first objection is a kind of epistemological objection. Why think that the why extend why think that the fact that the Mentaculus explains thermodynamical regularities should give us reason to believe the other probability attributions it makes? Actually, what time should I stop? So I should. How much more time do you think I have, Paul?
Paula?
That's like, yeah, you can go on for 10 minutes, let's say.
10 minutes, 10 minutes, I think I can get basically to the main points. Okay, so that's one objection. Here's a passage I took from a paper by Dustin stating this. reason of time, I'll just leave it, and the fact that my voice is going, I'll just leave it on the screen for 2 seconds while you read it and go on to the second objection, which I think is stronger and more interesting. Oops, maybe it's made in this thing too. Yeah, sorry. So this is the second objection here. Okay, it's that, look, assigning probabilities to individual events, like a woman being elected president of the United States in 2028, doesn't even make sense. Okay, individual token events don't even have probabilities. Now, this is sometimes said by people who hold various kinds of frequency accounts of probability, because frequencies depend on there being a frequency of a kind of event under a certain kind of circumstance, and a particular event will fall into many classes. Okay, and that's right. So individual token probabilities might make sense, or they do make sense, under a token propensity account of probability. But if you hold a frequency account of probability, which might be required if you think that the fundamental laws are deterministic, if you have an objective account of probability, at least that's the usual view, then it looks like that these token probabilities don't even make sense. In any case, Dustin is asking in this quote, what in the world do probabilities mean in the Humean Mentaculus? And why in the world should they have anything to do with what we believe or guiding our behavior, as probabilities do? And a similar objection is made by Mario. Okay, he puts it quite nicely. It's not immediately clear what the physical meaning of single case probabilities are in the Humean theory. Let's say there are the 2 coins, and the Mentaculus assigns a probability of landing heads of 0.4 to one coin and 0.6 to the other. Each coin is just tossed once and then destroyed. So what in the world can these numbers 0.4 and 0.6 mean? 0.6 mean? These probabilities, indeed influenced by the principle and an agent's attitude and behavior toward the outcome of the coin tosses. Okay. But it seems, however, that these single case probabilities need also to say something about the physical events themselves, as they would, for example, on a propensity theory. If they're going to have any physical meaning, if they're really going to guide an agent's degrees of belief. So that's Mario says. Okay, so let me give you my response. Okay, first, the objection that there are many probability distributions that validate probabilistic versions of the second law. Well, it's not clear that every single one of those probability distributions will validate sort of more sophisticated and detailed thermodynamic regularities. For example, those specifying the length of time it takes for a system of a certain size or structure and certain thermodynamic properties to reach equilibrium, and functional relations between the time it takes to reach equilibrium, the time it takes for entropy to change and entropy, or rates of changes of temperature in various regions, and so on. So I think that while there may be many probability distributions, all those continuous with the Louisville distribution, which will validate the gross form of the second law, that entropy will increase, they won't all agree on the rate at which they increase and on other thermodynamic regularities. I'm interested to see whether you all who know more about this than I do will agree with that. Okay. So there may be a limited class of probability distributions that capture all of the regularities that are really in thermodynamics. I'm not saying all of them are interesting or have been investigated, but there may be just a limited class of probability distributions that to these. And to the extent that propositions expressed in non-thermodynamic, to the extent that propositions expressed in non-thermodynamic language, it should say, supervene on thermodynamic conditions, the probabilities of these propositions will be specified as well. Okay, here's my response to the question about meaning. And this is really the main point that I make in my talk. Humean best system probabilities come together with laws as a package. Because of the intimate connection between laws and probabilities are involved in counterfactuals, the best system implies conditional probabilities that support counterfactuals. Okay, so it's not just being accurate about the outcomes of experiments or observations that are right, that is being captured by the Mentaculus, but also counterfactuals are being captured. On the BSA, it's the role of probability not just to accurately capture regularities, as Dustin says, but also to sustain counterfactuals. To accomplish this, the best system aims not only for accuracy, but for lawful accuracy. If probabilities aim only for accuracy, then the most accurate distribution be the one that assigned probability 1 to the actual microhistory of the universe. And this would result in a system that, while assigning probability 1 to all true regularities, including the thermodynamic ones, doesn't say which are laws and doesn't say what would happen in counterfactual situations. On a Humean best system account, accuracy is balanced against other lawmaking scientific criteria like simplicity. And this is very much involved in why it supports laws, why there are laws and why they support counterfactuals. If the best system of the world assigns a certain probability to a woman being elected president in 2028, as the Mentaculus does, given the current macro conditions, as the Mentaculus does, then this means that this is the best estimate of whether or not a woman will be elected given these macro conditions that follows by law. That's an important point. When the Mentaculus assigns a conditional probability to an allegedly unrepeatable event, given certain conditions, it says that this is the most accurate lawful estimate of whether or not that event will occur given these conditions. So that's the meaning given by the Humean account to these single case probabilities. Okay, so that's pushing back against the criticism that they don't have probability. Okay, and I think that this is because these probabilities are given by law. That's the reason that for them to guide one's beliefs. Why they should guide one's beliefs exactly by the principle, that needs some further argumentation, okay, which I'm not giving in this talk, but we can talk about it in the discussion. Okay, so this defense of the Mentaculus that I just gave against the criticism depends very much on a Humean account of laws. And I think it's likely that Dustin and Mario reject Humeanism. And for this reason, they reject the Mentaculus. In fact, it seems that Humeanism and probabilistic accounts of statistical mechanics naturally go together, as do Humeanism and typicality. And I suspect that the Typicalus are also, that advocates of the Typicalus are also anti-Humeans about laws and chances. Okay, now it turns out that, in fact, I do think that the Typicalus itself is committed to something like the probability of a female president, not the particular event of a female president being elected in 2028, but rather a conditional probability like, under such and such and such and such conditions, the probability of there being a female president elected at a certain length of time after those conditions obtained is such and such. And the reason is that this can be considered as something on an analogy to coin tossing. Of course, it's different from coin tossing in important ways. One is that it may not be that there are long sequences of those conditions holding, followed by whether or not a female president is elected or not within a certain length of time. But in the vastness of our universe, particularly if our universe may go on for a very, 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 very long time, it's not so outlandish to think that these conditions do occur over and over again. Okay, and if so, then one could generate out of that frequency probabilities of the Typicalus kind. And if one is willing to make a move from frequency probabilities to probabilities of token events, then the Typicalus would end up with those probabilities as well. Okay, so are these two accounts friends or foes? Well, here's one thing to look at them. When you look at them, they're really not inconsistent with each other. They differ with respect to SP and TP, that's for sure. And they both employ the Louisville measure, but they interpret it differently. And to do this, they offer different but perfectly compatible explanations of thermodynamic behavior. One could believe both of these, both that thermodynamic behavior is typical and that it's probable. As far as I can see, these explanations are compatible. They're even complementary in that I think that it could be argued that they really need each other. The Mentaculus invokes the PP to license the inference from it's very probable that ice cubes in warm water to melt to a high degree of credence that ice cubes in warm water will melt, while the Typicalus invokes Cournot's principle to license the inference from it's typical that ice cubes in warm water will melt to ice cubes in warm water will melt. As proponents of typicality emphasize, F's being typical in S doesn't mean that it's probable that a selected S is F. One cannot conclude just from the fact that crows are typically black that the next crow you see will likely to be black. You need some assumption like that each member of S that's going to be in the selection is likely to be selected as each other. So I think that in order to really underlying the use of this Cournot's principle, there is an assumption of probability that's being made. And I think that there's a similar argument that might be made that you can give a justification of the principal by employing Cournot's principle. I'm not going to go into that right now. So I think that these accounts may really fit together with each other pretty well. Okay, but there are two big differences between them that I mentioned earlier. One is that the SP is an empirical law that's separate from the dynamical laws, while the TP is close to being an a priori principle that's derived in some a priori from the dynamical laws. Now, still there's no incompatibility in interpreting both. So in the end, I conclude that the Mentaculus and the Typicalus can coexist, even though for Humeans and non-Humean, even it can coexist for Humeans. Non-Humeans will need to find some other account of probability if they want to embrace the Mentaculus as it's stated, because they're not going to buy the Lewis account of Humean account of probability. But what I suspect is that advocates of either one of these approaches will think they have no need for the other one to explain thermodynamics. So even though they're compatible with each other, each one from each perspective seems to be sufficient providing explanations. And I don't see that there's anything like a knockdown argument from either side against the other one. That's the end. Thanks.
Thank you very, very much for this very interesting talk. So let me open, yeah, thanks. So let me open it up to the talk. So please, if you have a question, you can use the button to raise the hand, and otherwise, I mean, I also have a question, so maybe I can start.
Okay, Paula.
So when whenever I come across the Humean account of laws, I wonder why, when you have the Humean mosaic, I mean, this is not exactly to the talk, but maybe more general. Then, I mean, when you have the Humean mosaic, which is like a random pattern of events, why do you have, why should you find any laws? I mean, why are there really regularities that would fit to make a law? I mean, why should...
So I'm not the right person to ask. The right person to ask is God.
But don't you think that...
That's our world. That's our world. Now, if you ask why we're finding it, first of all, using the word random there from Humean perspective is completely mistaken. There's nothing random about it, because random doesn't even make sense until you have probabilities and you have a system which specifies what probabilities are. Okay, I know why you're saying that. Here's another way to put what you're saying. Why should we find any regularities at all? Okay, I do agree that that's a question. But the Humean can ask the anti-Humean, why should we find any anti-Humean laws in the world? Why should we find any governing laws? Because you got to ask God about that one too.
But doesn't the fact that you find regularities somehow give you a hint on the ontology or some hint on the existence of laws? You don't think so?
Well, there are a lot of people who are going to think that, and they're not going to like what I'm going to say now, but I'll say it anyway. Yes, they're going to think that, and that has to do with the origin of the concept laws. Okay, so this has been studied in some detail by historians of science. It's a particular person, Peter Harrison, who I've learned a fair amount from, I have in mind, but there are other people too. And the notion of a law of nature really came to be the center of discussion in physics and philosophy only in the 16th and 17th century. And it's usually attributed to Descartes' Le Monde to make this a widespread notion, although he picked it up from other people around him, including Galileo. And he thought of laws as just being God's commands. This is how God is commanding matter to move. And I do think that that's the notion of law, and why the notion of governing is used connected with the notion of laws. And even people, long after they give up on God having anything to do with it, still use this metaphor, but it's frankly metaphorical. And I think that that's still in the back of your mind when you're asking that question.
Okay. Mm-hmm. Thank you.
I told you won't like.
I know that the laws started with God, but okay, so let's have the next question. Lev, you were first, I think.
Thank you, Barry, for your answer to Paula. So I can ask you what's human and not human in a simple way. In my understanding of your answer, or maybe the whole story, is that there is this, God had two options. First option, he can create a mosaic on a space-time. And then and trying to put some regularities in making this mosaic. Or he could create just a slice in particular time and add a few laws. And it seems to me that the second option, it's much, much simpler. And this is what scientists believe is happening. So this is what you called anti-human, but I would not call it anti-human. I think it's kind of a normal. So the anti-normal, it's human. Or maybe I'm...
Human or Humean. But anyway, so it's Humean. Okay, Lev, that's a great question. It gives me first of all, first thing to say about it is that, look, God is omnipotent. He's not constrained by simplicity. And he has all the time in the world, okay? Now, it might be that physicists are constrained by wanting to have simplicity. That's why physicists look to find axioms which could systematize the world, but God isn't constrained. Okay, but your question gives me the opportunity to tell this little story. I'm going to take up time for questioners, but I can't resist this. One or two people in the audience I see have heard this story, but a lot of you haven't. So I was once I heard the story because they were present when this happened. I was at a conference in Berlin, outside of Berlin. I think it's the Einstein whatever they call it, thing outside of Berlin, in Potsdam, with some philosophers and physicists. And I wanted to give a description between the Humean and anti-Humean views. And so I said it exactly the way that you said, Lev. I gave exactly the two accounts, just as you gave them. Here were two things that God might have done to create the universe. One, to illustrate the anti-Humean view. That was your second. And the first, to introduce the Humean one. Okay, so this was written about in the German newspaper because there was some well-known physicists there, so they sent some journalists. And I don't read German, so I took the newspaper back to Budapest and showed it to my wife's mother, who's fluent in German. So she started reading it, and she started laughing hysterically. And she said, it says here that the next speaker was the theologian, Barry Loewer, who talked about God. So I liked your way of asking it. But I don't think that the reason that it's simpler is a reason to think that that's the way our universe is. I don't think one should read the metaphysics of our universe off of the fact that it's being simpler. I do think one should read what the laws are of the fact that we want our laws to be simple.
I'm not sure I agree with you that if you are really theology or whatever, I think people will believe easier to omnipotent who doesn't have to make so difficult task. So the omnipotent, it's too cheap way out. Whatever, everything goes. I think if there is God, it has to be not something.
Lev, tell me, how do laws do their work? How do God's laws actually take the state at one moment and produce the state at the next moment?
Because there are particles. These particles create fields. These fields propagate and affect other particles.
But they propagate.
And there is entanglement in the superposition. All these things happening in quantum superposition. This is the world. This is the whole story.
Okay, you're bringing up something I didn't bring up in my talk. There's another way of being anti-Humean, and it sounds to me that you're being anti-Humean in this other way. And that is to say that, look, God didn't create laws and the matter or the fields, and the laws govern them. Rather, God created matter and fields, which by their very nature propagate, produce further. That's a different story. And that is a story that some people have about laws. So on this view, laws are not separate and over and above the universe governing it. Rather, in a certain way, the very fundamental ontology or properties in the universe are by their very nature not categorical, as Lewis thinks, but they're, you might call it, dispositional. And that is another way of being anti-Humean. It's just very difficult to tell that story so that it fits in with the laws of physics that describe how the state of the whole universe evolves. But this is a little bit of a long argument, so I don't know if we want to get into it right now.
Just maybe one.
It's another way. It's another metaphysics of laws.
But maybe just one sentence. I think God creates matter together with interaction. And there is this joke that Engel said that physicists found the basic equation of the world, and he said, please add another nonlinear term. So I think God makes both matter and the interaction.
Do I get the last word because I gave the talk? If you're a metaphysician, you want to know what are these things? What is there fundamentally in the universe? On the view that I was describing, in the universe are matter, fields, and also laws. And the laws do something to the matter and the fields. They evolve the matter and the field. They govern them. That was the view I was describing. Your view now, I'm not sure what it is, what your metaphysics really is, whether it's that or whether it's this other view that says that the fundamental ontology and properties are by their very nature have this kind of disposition to produce further instantiations of properties.
So, but I don't want to continue. So, but
Here we go on with the next.
Oh, you love, we see each other all the time. We can argue about this later.
thank you.
Let's go on. The next question was by Chris.
All right, thank you. Hi, Barry. So thanks for that talk. I was trying to get my head around the objection about the meaning of probability statements in the Mentaculus. And it might be because my connection dropped out for part of it, so I'm sorry if I missed something important there. But I mean, here's a way of asking it. Suppose I adopted your PDA and I thought even like, you know, the fundamental properties, like maybe mass or charge or something like that, was also part of the best system and determined by the best system. Would there be a similar question about the meaning of attributions of mass and charge? I don't really know how I would answer that if someone pressed me, like, what is the meaning of saying that such and such an electron has such and such charge? I never thought about worrying about that before, though. So maybe I'm just not getting something here.
So I'm not sure I understand the question, but you're actually asking a question about a different paper, which in some ways, for me, might be more appropriate for the laws, this laws series. But that's about my modification of Lewis's account. So the question, though, was about the meaning of probability. And I am thinking, and you're pointing out that the way probability is given meaning in Lewis's account is similar to the way I'm proposing giving meaning to fundamental properties in the PDA account. Does that seem?
Yeah, right. That I never sort of worried about what the meaning of an attribution of, say, mass would be in the PDA, but maybe either I should be worried about that if there's a worry about the probability attributions, or I shouldn't be worried about either one, it seems to me.
I think that's a really good question. I have to say I hadn't really thought about the similarity there and having to say something about it. And also, since most people here don't really know what's going on in the PDA, so we really haven't talked about that. Probably the best thing I could say is that we should continue this discussion.
Sure.
That I'll think more about your question, because I think it's a really good thing for me to think about how the notion of probability is going to be different from fundamental properties within the context of this view that I call the PDA. And
sure. All right. Well, thank you.
But I appreciate the question. I thank you for it.
Okay, so the next question is by Sylvia.
Hi, hi Barry. Thank you for the talk. I'm mainly sympathetic with your approach, but still there were two small questions I would like to ask you. And the first one was about the way you attribute to the people who write on typicality that they are using Cournot's principle. It surprised me somewhat because the formulation of it that I know is in terms of probability, namely that low probability events simply do not happen. But then I was wondering, do they really apply it, or is this perhaps a straw man? Because if typicality outcomes are still come with sort of a fallibility claim, like typically but fallibly or something, then yeah, I think that claim is too strong, perhaps, but I don't know the literature, so I'm asking it. And then the other thing I was wondering about, and I'm not sure it's completely clear in my head yet, but I just wanted to share the intuition, was that perhaps if you want to convince someone who is already on board with the Neuville measure and typicality that they could do more than just typicality assignments, I was wondering, does it help if you go to scenarios where there is repetition? Because if you have something that is true most of the time, if you repeat that many times, typically you will see something atypical. And I think there you're really close to the notion of probability. So obviously picking initial conditions is like a typical one case event. So there it doesn't come up naturally. But I do think there are other cases where the road to probability might be easier to walk or something like that. So that is what I wanted to discuss.
I'm glad to meet you. I follow things that you say, and so it's good. Maybe we meet in person sometime once COVID is over at any rate. Okay, the second thing that you said, I thought I said in my talk. Okay.
With the coin tossing, you meant?
Yeah.
But there,
And
it's the whole sequence.
and then at the
Yeah.
very end, I said you can generalize this to lots of other cases. Okay, at any rate, in a paper version of this, I'll go into that. But I completely agree with that. As to the first point, yes, you're completely right about Cournot's principle. Well, I have a colleague, I'm not sure he came to this or not, because I sent him, but he's a big fan. This is Glenn Schaefer, you may know. And he's a big fan of Cournot's principle. And I hear about it all the time from him. And of course, one of the issues about Cournot's principle is he has a paper I've seen from him in which he has about 20 different statements of Cournot's principle by Cournot and many other people. They all say slightly different things. And I once asked a person who I often ask about probability when I want to know things, that's Al Hayek, who I also might be here, probably not because he's in Australia. And he said, Cournot's principle is crazy. Nobody knows what it says, okay? But usually it is formulated with probability in just the way that you said. What I hope I said in my talk is not that it is Cournot's principle, but I might have, because I was rushed. I meant to say it's akin, similar to Cournot's principle. Okay, but you're right, Cournot's principle is stated with probability, but it's like it because it's saying that there's a certain feature of a type of event, and then going from that to saying that the event will occur. Okay. There's another feature it has that, for example, that Tim Maudlin likes to emphasize is that, which is a different kind of principle. It says, look, when it's typical, you don't need any more explanation of it. And maybe that's a more central or fundamental way of characterizing what typicality is.
Yeah, in that case, it doesn't sound very fallible, of course. Then the way out is gone. That I saw that's perhaps the, yeah, I will read on it more. Thank you in any case for pointing this out.
Okay, so we have now two more questions or comments. First one is by Tim.
Yeah, and part of it is connected to what Barry just attributed correctly to me.
I didn't realize you were here. Hi.
Hi. And I guess I just want to ask something, because I think both Paula and Lev were, raising a question that comes up over and over again in this. And let me try and do it in a, I think, reasonably sharp way, just to get your response. So you have this picture of a mosaic, and well, it's not like a kind of mosaic with different shaped pieces and only certain pieces fit in. So it's more like a grid, or at least imagine there is a finite, just because there are issues with infinity here that I don't think are relevant, just a kind of finite four-dimensional grid, yeah? And each pixel, as it were, in this grid has some finite number of states it can be in. And you think of these as the particular values that the perfectly natural properties, local properties could have. So if all of this were finite, some large number, huge number, doesn't matter, but finite, then you really could make a sharp statement about what is typically the case with respect to all the possible mosaics, right? And what would be true, I take it, is that it would typically be the case that a typical mosaic would show no macroscopic pattern at all. It would just be noise, right? It would just be no, there would be nothing macroscopic. And you could try and make this computational, whatever, but you get the idea, because that is what happens on TV screens and stuff like that. When, as we say, they're being random, the pixels are being randomly fired. Now, from this idea that you say, look, from a typicality account, things that are typical don't require any further explanation, and things that are atypical do, right? Atypicality is an indicator that you haven't got everything. I think this gives the idea, you say, well, gee, our pattern, our actual mosaic is really atypical with respect to this thought. A typical one just wouldn't have people or planets or anything, pretty much, except mush. And And that means that there ought to be something there explaining why there are these patterns. And then you say, the laws explain the patterns, at least if you believe the laws are something separate. Whereas the Humean, like you said, I mean, your actual response was ask God, which I can't do because I don't believe there's a God to ask. I mean, I don't understand. I don't want to bring God into this. There ain't no God, right? We're trying to actually explain the world we live in without a God. And so I'm still, I think, puzzled about how you think about this, right? You seem to want to say there is no puzzle there about why we have such an amazingly structured world transtemporally with all this pattern in it, when at least in the finite case, in a very strict way, that would be really, really, really atypical.
So I do think you raised it more sharply, and that's good and helpful. I don't think that there's no puzzle there. That wasn't my view. My view is that bringing laws in don't help alleviate the puzzle that I see that's there, because I have the same kind of puzzle about laws. In fact, I don't know exactly how you're thinking about the fundamental ontology or possible ontologies for possible universes. But I guess there are TV screens in which there's just mush, and there are TV screens in which there are some sort of device, laws, let's say, that produce, I forget, somebody earlier was bringing up some sitcom, I guess before we started, produce, the sitcom. Well, often they seem to be mush too, but I guess, at any rate, that's right. But look, of all the possible TVs there are, some of them have laws and some of them don't. Most of the TVs maybe don't have any of them. So I'd still have the question, why did I get a TV which shows, what we're thinking of as, what you're thinking of as regular patterns on it, as opposed to one of these TVs which doesn't? Now, there might be an explanation that what's within our world, employing the laws of our world, but here we're talking about the fundamental metaphysics of the world. And I don't see, so really what I'm saying is this, maybe I put it by metaphorically, wasn't the clearest way to say it. Look, the question is this: of all the possible ways that could be, there are lots of worlds without laws and lots of worlds with laws.
Yeah, I don't know. I mean, that's a case where I really don't understand. I mean, I'm not sure if there are laws. I even think it's metaphysically possible that there not be laws. I'm not sure that metaphysical possibility goes beyond physical possibility, and I take physical possibility to be that which is consistent with there being the laws that there are.
Well, that's what you think. I can agree with that. I think if I say that metaphysical possibility doesn't go beyond physical possibility, and I could also say, look, all its physical possible are they what's consistent with the laws of our world.
Yeah, but look, this is inverting. I mean, the issue is between the entire four-dimensional mosaic and the laws on any view, which is more explanatorily fundamental, right? Or which is more metaphysically fundamental. The question is, Lev's picture and my picture is that it's the obtaining of the laws that explains the patterns. And on, as I understand it, your picture and Lewis's picture, it's the obtaining of the pattern that accounts for the laws.
As you know,
this is just a fundamental kind of Euthyphro, what explains what issue.
Well, as you know,
I don't understand how it goes on your thing, but
because we've engaged in this before, my response is there are two notions of explanation involved in this. There's a scientific explanation in which the laws scientifically explain aspects of the patterns in terms of other aspects of the patterns. The law is also explained by unifying the patterns. There's a metaphysical explanation, which is what Lewis is talking about, in which the patterns metaphysically explain the laws.
Okay, so we've had this, but maybe it's useful for people to say, and I'll just end with this comment, right? I'm somebody who doesn't want there to be a distinction between science and metaphysics, right? I think of metaphysics as informed by science and responsible to it and so on, and not some other kind of discipline. And so I think the need in your response to make a rather sharp distinction there is something at least people should consider when they're trying to decide which way they have of thinking about this. So I'll just leave it there.
Okay, but I get the last word since I guess.
Yeah.
Okay, so there is this other stuff I've done, which maybe we really haven't talked about at all because it's been cooking around with me for about 10 years, but I haven't really been exposing it. And I've published a little bit of it, but not that much. And we haven't been talking so much recently. This modification of Lewis's account, which is much closer to the idea that there's not a separation between metaphysics and science. And it also has something to say about the very issue that we're talking about right now. And the idea that in this other approach to it is Humean in a sense, in this respect. What it does is it says, look, what we're interested in is coming up with the best systematization. And the best systematization might include both laws and fundamental properties together. And what they're supposed to do is capture something like the macroscopic regularities of our world. So that's the kind of given, but they're not metaphysically given. And what's going to be fundamental in this account is what ideal science would end up producing. And that will be both metaphysically and physically fundamental. But we should really meet up and have a discussion of it, because I'll send you what's written about this now, because I'd really be interested in what you think about it. We should talk about it. Okay, good.
Okay, thank you. So let's have the last question before we go on with the next talk. So Mario, you have another question.
Yes, thank you. I have a question that's basically going in the same direction, and a follow-up on what you said, Paula, about the regularities in the Humean mosaic, where Barry said the answer would be ask God. So I want to dig deeper in this God metaphor, which I think, according to Barry, would be the same answer for a non-Humean account. But I think in the Humean case, you cannot say ask God. I think that's not an answer, because in the non-Humean case, you can say God created something like laws or dispositions or something, some modal connections that constrain what is happening in the world. And in the Humean case, the only thing that God does is just creating the mosaic, and then the mosaic is left by itself. So you cannot say for the existence of regularities, ask God what he did, because he couldn't do anything. He could just set the initial conditions, and there's no further constraints or anything that he could do. So what would you say, Barry, to that reply?
I think what you said is right. I think it's what I was saying too, that these are the two different pictures that you just described. And it's right that God would, in a sense, have to do more. Maybe I didn't say this, but I should have said this to Lev. And it's in one way, God has to do more and less on each one of these. On the Humean account, God has to do more because he has to fill up all of space-time. Okay, but he also has to do less because he doesn't have to create any modal stuff. Okay. On the other hand, on the anti-Humean account, he has to do more because he has to create all the modal stuff and make the modal stuff do this other work. The reason that one wants to be Humean, really, deep down in me, is I just don't understand how the modal stuff does its work.
But wouldn't you also, but I mean, the natural reply would then, there is something that needs to be explained. There's some kind of a gap or something that these regularities that somehow are in the Humean case unexplained. I mean, you may be dissatisfied with the explanation in the non-Humean case, but in the Humean case, there is just no explanation. This I think, what people are bothered about, that there's something going on that in some way speaks for an explanation.
My response to it, which in the discussion I just had with Tim, it led to being the case when we argued this over a little bit, to my wanting to defend the view by making a distinction between metaphysical explanation and scientific explanation, and Tim saying, well, if you collapse that distinction, I won't be able to make that defense. And I think he's right about that. Okay, but if you make that distinction, then there is an answer to what you're saying. Look, there's no metaphysical explanation of the laws. Still, the laws are just, you got to ask God where they came from.
Yeah, but even God cannot answer that. I mean, they just came contingently. They're just there.
God can answer. I mean, if you believe this, God can answer it. So no, my point to you is, I'm not sure it's coming across so clearly. My point to you is that, look, the anti-Humean still has a question about why the world is that way. Why does it have this modal stuff in it? It's right that he's put modal stuff in it, which enables him to give something like an explanation about why they're the patterns that there are. That's a scientific explanation. And what I'm saying is, I don't really understand, or the Humean doesn't understand, how that really works, how that modal stuff is able to do that explaining. I think this is one of those places where people some people think, gee, I'm going to make a terrible comparison, but when you see different people political sides of things, I don't want to get into American politics. One side just doesn't understand why the other people, I've run into people who don't see that Trump is such an idiot, and how can such a buffoon be taken seriously? I've actually run into people like that. I'm not saying that I'm like that or that you're like that, but that's, in a way, there are philosophical issues where I would like to have an account of the fundamental metaphysics of the world, which just doesn't have modality at the bottom, because I don't see how it works.
Okay, so maybe we can put this to the general discussion in the end.
Okay, sorry, Paula.
Sure that.
So I think it's now time to really, let's thank you again, Barry.
Can I just say one thing quickly to Mario before you do it? Hey, Mario, I'm going to be in California at the end of the month. If you're there, maybe we can meet up.
That would be great. Yes, I also have to reply to one of your emails and so on. So
Okay.
thank you. Yeah.
Let's thank you again, Barry.
Yeah, thanks to everybody. Thanks for the questions that you
let's go on to the second talk. So Dustin, I think, is going to say something to these issues as well. So next speaker is Dustin Lazarovici, who is from the University of Lausanne in Switzerland. He obtained a PhD in mathematical physics in Munich and one PhD in philosophy in Lausanne. He's now a postdoc and is going to move to Haifa and go to the Technion. So I'm happy that you're here, and you will talk about typicality as a way of reasoning in physics. So please.
Yeah, thank you very much. So while I'm trying to share my screen, let me say that I'm very honored to be invited here and speak after Barry Loewer. Maybe also make certain counterpoints to the view articulated by Barry Loewer. And although I take, full blame for the particular things I'm saying today, I can't take too much credit, because a lot of the ideas are things I learned or gathered from people like Detlef Dürr and Shelley Goldstein, Nino Zanghi, Tim Maudlin, Glenn Schaefer, but also from more confrontational discussions with Barry Loewer or David Albert or Jeff Barrett. So I noticed that I didn't have really references on my slides, so I thought I should say that from the very beginning. Do you see my screen?
Yes, yes, perfect.
Okay. So I agree with Barry that we actually agree on a lot. Maybe we even agree on everything that a physicist has to care about in her daily work. And of course, that's because a lot of what we agree upon is Boltzmann's view on statistical mechanics. And but we also agree, for instance, on the very limited extent to which notions like knowledge or uncertainty or like epistemic uncertainty or information, to the very limited degree that they play a role in really accounting for thermodynamic or other physical phenomena. So let me, from my point of view, highlight the basic issue that I think we also agree upon. So there are certain macroscopic regularities in the world. Like here are 3 of them as an example, like that apples fall from trees to the ground, but don't spontaneously jump up, or that rocks thrown on Earth fly along roughly parabolic trajectories, or that the relative frequency of heads in a long series of fang coin tosses comes out approximately 1/2. Right? So these regularities are of a different kind. So the first one is actually an instance of the second law of thermodynamics, although not evidently so. The second appears like a deterministic mechanical phenomenon. The third is a statistical regularity, right? But all of these regularities strike us in some sense as law-like. They may even be among the more basic experiences that we have that found our belief in a lawful cosmos. However, we also agree on the fact that all these macroscopic regularities must be explained on the basis of more fundamental microscopic laws. And then it turns out that even an apple or a rock consists of a huge number of microscopic particles, like the relevant order of magnitude is always given by Avogadro's constant, so approximately 10 to the power of 24 particles. And due to to this huge number of degrees of freedom and the relatively chaotic dynamics of these microscopic constituents, it turns out that the microscopic laws put very few constraints on what is possible on macroscopic scales. So David Albert has this very beautiful quote, putting it very succinctly. Note that nothing whatsoever in the Newtonian law of motion, together with the laws of the interparticle forces, is going to stand in the way of that rock suddenly ejecting one of its trillions of elementary particulate constituents at enormous speed and careening off in an altogether different direction, or for that matter, spontaneously disassembling itself into statuettes of the British royal family, or, come to think of it, reciting the Gettysburg Address. So David Albert, if you don't know him, you might have gathered from Barry's talk that he's firmly in Barry's camp. So obviously we are in perfect agreement on what he's saying here, just that the fundamental microscopic dynamical laws themselves, they actually put barely any constraints on possible phenomena on macroscopic scales, right? So we need some additional principle or mode of inference from the fundamental microscopic laws to macroscopic regularities, notably other than solving the exact equations of motions for the exact initial condition of our universe to determine the exact microhistory of our universe. But that's not just an issue of ignorance, that we cannot do that, right? That we don't have epistemic access to the exact initial conditions of our universe, or that even if we have, the problem would be mathematically too complex to solve. All this is true, but not exactly to the point. Even if we were Laplacian demons and could verify that the dynamical laws plus initial condition make, for instance, the second law of thermodynamics true in our universe, we shouldn't be satisfied with that. It would still be unsatisfying if such law-like regularities turned out to be completely accidental, like contingent on the very particular fine-tuned initial conditions of our universe. So even the Laplacian demon would really learn something new and important if he learned that these regularities that we observe in the world, right, they do not obtain for all initial conditions, but they obtain for nearly all possible initial conditions of the universe, right? So they are not necessary, but they are typical, as I would say. And the first part, I guess, Barry would say too, although he might mean something slightly different by typical. And this is something that really clarifies the relation between the fundamental laws and the macroscopic regularities, right? It's not about the fact that the regularities obtain for the exact initial condition of our universe and that we don't have precise knowledge of the initial condition, right? That's not really the point. And the statement that really clarifies the status of these macroscopic regularities are typicality statements of that kind, that the regularities obtain, as I would put it, for nearly all possible initial conditions of the universe. And I'm usually a bit cavalier about the fact I noticed after one of Barry's remarks, of course, that the typicality might have to be conditioned on some macroscopic boundary conditions. For example, the past hypothesis, the special low entropy beginning of our universe, or if you care about statistical regularities in coin tosses, you might want to condition on the fact that there exist coins to begin with, and so on. But still then conditioned on certain macroscopic boundary conditions, nearly all possible initial conditions lead to the instantiation of certain regularities in the world. Right? And it kind of always seemed to me immediately intuitively compelling that if you could establish that, then you are done. I mean, what else is there to worry about if you can establish that a certain phenomena that we observe in the world is typical, that is the kind of phenomena that according to the fundamental laws would obtain for nearly all possible initial conditions. But after a while and many discussion with philosophers, I realized that, well, I need to be more explicit about why I think we are done, because logically, it doesn't follow from the fact that something is true for nearly all possible initial conditions or nearly all nomologically possible worlds that is therefore true in our world. So really, when I'm saying we are done, this is based on a rationality principle for which formulation I'm drawing a lot from Tim Maudlin. So the rationality principle associated with typicality is roughly this. If a feature of our world is typical according to our theory, there's nothing left to explain, right? It is irrational to wonder further why our world is in that particular respect like nearly all possible worlds that the theory describes. So nearly all possible worlds that are allowed by the fundamental laws postulated by that theory. On the other hand, if a salient feature of our world is atypical according to our theory, then this is something that cries out for further explanation. And in the last resort, we should revise or reject the theory if no additional explanation of that atypical phenomenon can be found. Now, I smuggled in here a word, a salient feature of our world. That is because there's a subtlety and a challenge associated with this principle, because in particular, as we go to a more fine-grained description of the world, any world is atypical with respect to certain properties, right? So any world, any universe certainly atypical with respect to its exact microstate, or our world is atypical with respect to the exact sequence of lottery numbers drawn in the past 50 years, or the exact number of stars in our solar system, right? So there are certain facts that are atypical, but don't really create this explanatory pressure, at least not in the sense of challenging this theory. So there are some facts that are acceptably brute, one could say. And I don't think there's a precise technical definition grasping all the characteristics of fact that warrant a kind of scientific explanation. But one qualification that I find useful is the following, that, you know, if you have a certain coarse graining, let's say given by a macro variable, right, the fact that for our universe f of x equals y, even if that's a typical, calls for an explanation only if a state of affairs that is not atypical would have been possible, right? So that's why, for instance, the actual macro state of the universe is an acceptably brute fact. Of course, the actual microstate of the universe is a set of measure 0, right? But any possible microstate, any other possible microstate would have been atypical as well. So this is something that I would call an acceptably brute fact. And I call for reasons that are not entirely obvious, but such cases where any possible outcome would have been atypical, I call them Morgenbesser cases. And that's because of an anecdote of the philosopher Sidney Morgenbesser, who's like famous for his very witty remarks. And one anecdote says that he responded to the ontological question, why is there something rather than nothing? Well, if there were nothing, you'd still be complaining. Right? And those are the cases where I would talk about acceptably brute facts. Well, if the microstate of our universe, or the exact sequence of lottery numbers, or the exact number of stars in our solar system would have been anything different, you could still be complaining. Right? So that's at least one additional qualification that I think takes care of not all, but a lot of these cases where we feel like an atypical event doesn't really call for an additional explanation. So there are also cases where I would speak of probability rather than typicality, right? But those this notion of probability in this under this typicality view applies in a different context. For instance, suppose we consider an ideal gas in a box. Let's think about it as our model universe. Okay, that has a certain microstate which comprises the exact position and velocity of all the n particles of the gas. Then you can prove, right? Then we consider the empirical distribution of the particle velocity. So with a slight abuse of notation, read this psi as an indicator function. And for any v here, this empirical distribution counts the fraction of particles whose velocity is in a small volume element dv around v. Then you can prove mathematically that for nearly all possible x, right, this empirical distribution is very close to a theoretical distribution that is known as the Maxwell or Maxwell-Boltzmann distribution, and which has this famous functional form. Right, so with a little less abuse of notation, you can prove a result of the following kind. So here, this would be the microcanonical measure, so just a stationary measure conditioned on the hypersurface of constant energy E, right? And then it says that the set of microstates X for which the empirical distribution, that is the fractions of particles whose velocity is in within a set A, right, of possible velocities, the difference between this empirical distribution and the number you would get by integrating the Maxwell distribution over A, right? The set of X for which these two quantities deviate by more than epsilon is very small for large n. So ideally, and you can derive an exact numerical estimate for this delta. Right, so this would be a more precise mathematical expression of a typicality statement. That typically the empirical distribution of velocities in an ideal gas, right, is close to the Maxwell distribution. Right? And with respect to this Maxwell distribution that approximates this Maxwell distribution that corresponds to the typical empirical distribution of particle velocities, here I would speak about probabilities. And the difference is here that our box exists only once. So the role of this measure, even though it's technically a probability measure, is only to tell us what obtains for an overwhelming majority of possible microstates of the system, right? This empirical distribution, as well as the Maxwell-Boltzmann distribution, they really refer to a statistical ensemble. namely to the actual velocity distribution of the great many particles that exist within a box. And this is very similar to how Boltzmann actually reasoned about it. Here, the famous quote that many of you will have seen 100 times already, but some maybe not yet. So Boltzmann argued that for the derivation of the Maxwell distribution, the ensuing most likely state is not an outstanding singular state opposite to which there are infinitely many more non-Maxwellian velocity distributions, but it is, to the contrary, distinguished by the fact that by far the largest number of all possible states have the characteristic properties of the Maxwellian distribution, and that compared to this number, the amount of possible velocity distributions that deviate significantly from Maxwell's is vanishingly small. Right, and another important result that I can't discuss in detail, but some of you will know, is the derivation of the Born rule in Bohmian mechanics as carried out by Detlef Dürr, Shelley Goldstein, and Nino Zanghi, where you can show that for typical initial configurations of a Bohmian universe, distribution of particle configurations in an ensemble of subsystems with conditional wave function phi is given by the phi squared density, so Born's rule. And here we have a mathematically nice but deductively somewhat unfortunate fact that the natural typicality measure here, in contrast to this case, where we had here the microcanonical measure as a typicality measure and the Maxwellian as the typical distribution, here in this case, the natural typicality measure has the same functional form, namely given by the psi square density in terms of the universal wave function as the typical distribution. Here, phi square with the phi square density in terms of the conditional or effective wave function of subsystems. Right, and for people who don't quite appreciate this difference, on the one hand, between a universal wave function and a conditional wave function of subsystems, and on the other hand, between a typicality measure and a typical statistical distribution, this sometimes gives rise to the objection that the argument is somehow circular. You put psi square in and psi square comes out. But it's the non-trivial feature really of the Bohmian dynamics that in this case, the natural typicality measure has the same functional form in terms of the universal wave function as the typical empirical distribution has in terms of the conditional wave function. So maybe something that God has arranged to punish people who don't pay attention to the conceptual distinction between the different concepts involved here. So in any case, it's something that I will stress more later, but that also Sylvia Van Marcus mentioned in her question, that this typicality view grounds a notion of probabilities as typical relative frequencies. Right, and I'll say a little more about that later. Now, as I said, Barry might agree with the first part of my statement that, well, the macroscopic regularities that we observe in the world are not necessary, but they are typical. So necessary means they would obtain for all possible initial conditions of the universe. That is not the case, right? But they are typical. However, by that, Barry means something like they obtain with very high probability. As opposed to my saying that they simply obtain for nearly all possible initial conditions. Right? And in general, you would worry, what sense could it even make to speak about probabilities in connection with the initial conditions of the universe? Right? You can't really, it doesn't really make sense to imagine an ensemble of universe with a statistical distribution of initial conditions, because the universe exists once and only once. It is what it is. And many people would fall back on epistemic or subjective probabilities. But Barry and I think, agree that this is beside the point, that our knowledge or ignorance or belief, right, couldn't really explain why concrete physical regularities hold in the world, right? So that heat always flows from the hotter to the colder body, right? It doesn't have anything to do with what I know or don't know about the initial conditions, right? But then Barry, with his Mentaculus theory and with David Lewis, with his version of David Lewis' Humean regularity theory of objective chance, right? He has a notion of probability that prima facie makes sense. Not just prima facie. It makes. Let me grant that it does make sense. It does make sense to have a Humean probability law over initial conditions of the universe, right? So this is the part of the challenge that I think Barry's account meets, or the Humean account in general does meet more or less satisfactorily. But there's then a more general question, right? You have this probability distribution on the past hypothesis macro region, let's say, the possible initial conditions of the universe. And as Barry said, it gives you probabilities or conditional probabilities for virtually all physical propositions about the world, like a probability that I will contract the coronavirus tomorrow, or probability that the United States elect a female president in 2028, conditioned on certain macroscopic boundary conditions again. And then the question that was also expressed beautifully in the quote from Mario that Barry showed is what does it even mean, right? What does the probability of an event A really tell us about the world? And there's a general dilemma here, right, and can be phrased roughly as follows. So only probabilistic facts follow from probability theory, but there are no genuine probability facts in the world, at least no concrete physical facts. The event A either happens or not, right? It doesn't happen like more strongly if we associate with it a higher probability. So it would follow from that no facts about the world follow from probability theory. Of course, this is not true, but the point is we need an additional principle, or if you are like a philosopher inclined to logical positivism, you might speak of a bridge law or a bridge principle that somehow connects probability statements, right, to concrete physical or empirical facts in the world. Right, and a standard principle would be like the frequent risk principle. If the probability of the event A equals B, then A will occur approximately P divided by n times on a large number of n trials. Okay, and this is the kind of principle. It reminds me a bit of, the laws of textbook quantum mechanics, that it's clear how to apply in certain very specific and controlled situations. In this case, if you make an actual random experiment and have the same coin, fair coin that you throw many times under constant conditions, but it doesn't really make sense in general. So in general, for an event, this is not clear how to embed a particular event into a statistical ensemble. So you could speak of frequencies, or whether an event such as the United States electing a female president in 2028, given the current macro state of the world or of American politics or whatever, that you could even embed it in a sufficiently large ensemble to make sense of this frequent risk principle. The other problem is, of course, that this principle doesn't really follow, or doesn't seem all that consistent with probability theory. Right? From probability theory, you can't really derive that if you have an event with probability A and repeat it many times, it will happen approximately P divided by n times, right? You can only derive that it will do so with high probability. And then if you ask, okay, what does this high probability now mean? And you want to apply the same frequent risk principle, then the whole thing becomes circular, of course. Then you would have to say, okay, then you have a large number of trials of the same random experiment, and in most of them you'll find, and so on. right? So that's one of the standard objections against frequentism in general, that it has this kind of circularity, right? So that you would have to say probability corresponds to relative frequency with high relative frequency, something like that. But I think it's fair to say that among philosophers, there's a pretty widespread agreement that this frequentist principle really does capture the empirical content, most of the empirical content of probability statements, but that's not tenable as a fundamental principle or interpretation of the meaning of probabilities. Right? Another principle is the principle by David Lewis, which I don't remember if Barry mentioned it explicitly, but I'm pretty sure he did, which is the kind of principle that is associated with Humean chances, which says that if the probability or conditional probability of an event is P, then your credence or degree of belief that A will occur should be P. And you may feel like that's not really an answer what the probability tells us about the world, right? Why does it speak about about credences or degrees of belief, right? I want to know, what does the probability tell me about the world that makes it rational to assign this degree of belief to the occurrence of A. But then if you speak to a brilliant philosopher like David Lewis or Barry Loewer, they may say something like, and I'm oversimplifying here, well, it tells you that the world is such that it is rational to assign the degree of belief P to A occurring. And you may still feel like this is not really addressing the question, and it seems kind of circular. And I think you are right, but it's a relatively subtle issue to make. And Barry mentioned some of the arguments and counter arguments that really go into more detail about debating the viability of this principle. And the final principle, or version of which I will endorse, was also mentioned by Barry and in a discussion by Sylvia, that would be Cournot's principle, which says that if the probability of an event is very small, so very near zero, then A will not occur on a single trial, right? And that is the kind of quote unquote bridge principle really then makes a sensible connection between probabilistic statements and facts in the world. If our theory assigns a very low probability to a particular event, the theory tells us this event will not happen. And also for the reasons that Sylvia mentions, this principle requires, again, certain qualifications, because a very low probability event is not impossible, and sometimes they do happen. So I think really the most plausible or the best formulation of Cournot's principle, at least in the context of physical theories, right, is again this rationality principle that I associated with typicality. If now you read typical as very high probability and atypical as very low probability, I would say it's really the same kind of rationality principle, right, that we would associate with probability statements, and then make the link from probabilities to the world. And I think it's very interesting that if we look at Kolmogorov himself, basically the father of modern axiomatic probability theory, he thought about this issue. What is really the link between probabilities and the world? And he has in his Grundbegriffe this chapter, Das Verhältnis zur Erfahrungswelt. So it's exactly called the link to the world of experience. And he basically puts down two principles. And the first principle is roughly the frequentist principle. Over many trials, the frequency of an event A approaches P of A. He's more careful about that. He says under appropriate conditions that he doesn't, he won't or can't explain in detail. This will be the case. And principle B, that on a single trial, if the probability of A is very small, then one can be practically certain that the event A will not occur. And it's not entirely clear. Glenn Schaefer also discusses this briefly in his really brilliant paper, The Sources of and Legacy of Kolmogorov's Grundbegriffe, why Kolmogorov included principle A. Because it seems somewhat redundant, because by the law of large numbers, right, principle A really follows from principle B in cases where principle A is justified, right? So in cases where this frequentist principle is justified, it follows from Cournot's principle. For instance, the most standard form of the weak law of large number. If we have here a family of identically distributed independent Bernoulli variables describing n trials of A, so xi is 1 if event A happens on the ith trial, and 0 if it doesn't happen. And then again, we have here an empirical distribution, right, counting the relative frequencies of occurrences of A. And then we will find by the weak law of large numbers that would vary, so that the probabilities that the relative frequency deviates significantly from the number P is very small. And probably arguably the reason why Kolmogorov still felt the need to include this principle A is that, of course, it does hold as a matter of fact in many cases in which we won't be able to prove a law of large numbers, right? Certainly not in this idealized form. Of course, this idealized form is just a very special, the most basic case of a law of large numbers. There's a great variety of possible laws of large numbers, or more generally speaking, concentration inequalities, which establish that typical values concentrate near a certain value. But my claim is that whenever this kind of frequency, this principle is appropriate and justified, right, a statement of this kind, that the typical relative frequencies are close to a certain number, which we then call the probability, must hold true, even though it can be awfully hard to prove. So in essence, I spent 4 years my entire PhD and thesis in mathematics proving a kind of law of large numbers for many particle systems, right? And of course, as also Sylvia said correctly, if I may call you Sylvia, in the end, in my view in particular, if we have genuinely probabilistic laws, right, I wouldn't apply Cournot's principle to probability, but statements like that would be genuine typicality statements telling us that for nearly all possible initial conditions, right, the relative frequency will be close to a certain number, right? And this typical relative frequency is what we would call then the probability. So again, this view then that probabilities are typical relative frequencies, right? But beyond that, if you have the fundamental measure on the phase space of the universe, as Barry explained, the exact number it assigns to any odd subset of phase space, right, has no physical significance, right? The measure, the typicality measure, is really just used to make more precise what we mean by typical, which sets of initial conditions are large, containing nearly all possible initial conditions, and which are very small, containing nearly none of the possible initial conditions. And then if you look here, there's a certain reason why I put here the number, just the number P and not P of A or somehow the expectation value, because at the end of the day, if you have such a statement, right, about typical relative frequencies, in this case, the typical relative frequency of the event A equals P, it doesn't matter anymore where this number P comes from, right? In particular, many other, the lowercase p, in particular, many other measures other than our typicality measure will agree on the smallness of the set and make a typicality statement of that kind true. So many different measures will agree on the fact that the set of initial conditions for which the relative frequency deviates significantly from P is very small. But I mean, Cournot's principle is really the version of typicality that is appropriate if we had genuinely stochastic laws, right? So suppose we have a fundamentally stochastic law that tells us that a coin lands on heads or tails with probability on 1/2. Or you may also think instead of spin measurements on a spin 1/2 particle, if you want an example of something that people are more accustomed to thinking as a fundamentally stochastic law, right? Then what the law does in effect is assign a probability or weight to possible histories of, in this case, coin toss outcomes. Right here, the possible histories for the first n trials. Right, but the stochastic law doesn't, again, in this case, put any constraints at all on the possible macro histories. Right, all conceivable sequences of coin toss outcomes are possible, and in this particular case, even equally likely. Right, so the law our actual history could be this one, where we observe first tails, heads, or this one, tails, heads, tails. But it could also be here, the lowest one, where heads comes out all the times, right? All of these possible macro histories, all of these macro histories are possible and in fact equally likely. So the question is, how does such a stochastic law have any kind of empirical content at all, right? How is it even informative about what happens in the world? And here again, Cournot's principle comes into play. And what we should take as the predictions of the theory, right? We should take the theory to predict the regularities to which it assigns a cumulative probability near 1. So here, why all conceivable macro histories have the same probability that will actually go to 0 if n is very large, right? The set, right, of all possible histories for which the relative frequency of heads and tails is approximately 1/2, will have a weight or probability of very nearly 1. And by Cournot's principle, or the version of Cournot's principle that I would endorse, this is really what we should take as the prediction of the theory, right? And then, a form of Cournot's principle is also the only possible way to falsify or reject such a theory, right? Because no conceivable outcome sequence is really forbidden by the theory. Right? The only rational and possible way to test the theory is to reject it if we observe phenomenon regularities that the theory deems very unlikely, so to which it assigns a probability very close to 1. Right? And that would be the case, for instance, here for macro histories in which head comes out almost all the time, or on many trials twice as often, tails and so on. Right, so here's the basically original quote by Cournot, establishes the Cournot principle. Unfortunately, it's not such a useful quote because the phrasing sounds wrong to at least to modern philosophers of science. But Cournot said a physically impossible event is one whose probability is infinitely small. So of course, physically, it's clear from the context of writing that he didn't mean by physically impossible what we would mean by physically impossible. Like one of his go-to examples is like a spherical cone standing perfectly balanced on its apex, which is not impossible. We just immediately see, just because of the geometry of the thing, that it's very atypical, right? But I think very good is the second part. This remark alone gives substance, an objective and phenomenological value to the mathematical theory of probability. Right? So Also very nice is the quote from Émile Borel. It's not a literal quote here, but he called this principle that an event with very small probability will not happen the only law of chance. And of course, again, if we read law as it's impossible for a very small probability event to happen, then the statement is too strong. But if we read here law, either in the sense of a bridge law connecting the probability calculus to physical predictions, or as a rationality principle in the form that I tried to formulate, and I think it's very nice. It's very nice and an appropriate quote. Right, so this all goes to the discussion that that Barry went into in much more detail and greater sophistication, whether these single case probabilities predicted by the Mentaculus are really physically meaningful, whether they really tell us anything about the world at all. And for reasons that Barry explained in much more detail than I have, I think that they do not. I think that all we need, then ultimately the physical and empirical and predictive content of probabilistic statements is always grounded in Cournot's principle, right? And therefore, thus I'm making the additional step that we don't really need a probability measure on the initial conditions of the universe. All we need is a typicality measure, a measure that grounds typicality statements, right? And understanding the typicality measure, not in terms of probability, but just in terms of telling us that a certain fact or feature of the world obtains from the overwhelming majority of possible initial conditions, I think that this rationality principle, a typical fact doesn't require additional explanation, has an immediate intuitive appeal, right? That it also wouldn't have if we, that at least for me, it wouldn't have if we explicated it in terms of probability. Right. So if I talked about Cournot's principle as a bridge law, as I said, that's like a concept or a term that comes from logical empiricism. And the problem with bridge laws in general is that it's not obvious. It seems like an ad hoc, sort of an ad hoc identification of certain theoretical terms with certain observational terms. There's not really an explanation. It's not really an explanation as to why this bridge principle should hold. For instance, in quantum mechanics, why is it that eigenvalues of an operator should have anything to do with measurable quantities in the world? So the kind of bridge principle is compelling if, but the kind of bridge principles are okay if they are immediately intuitively compelling, right? So in case, if you have in physics a primitive ontology, for instance, you wouldn't even feel the need to specify as a bridge principle that, you know, what the theory describes as the trajectory of a particle corresponds to the position of particle in physical space. It's true that one is a mathematical statement, the other is a physical statement, but the connection is immediately intuitively compelling. And I think this is similar for Cournot's principle when associated to this notion of typicality. Well, then Barry asked what determines the right typicality measure. And there are generally two answers given that I think are both true, but pull in somewhat opposite directions, at least different directions. One answer is that one doesn't have to worry too much, because in general, all reasonable measures will agree on what is typical or atypical. So Tim has this very nice example of someone saying the Sahara Desert is almost all sand. And someone asking, well, but by what measure do you mean? By surface area, or by volume, or by weight, or what do you mean? And then the answer is no, you don't understand. By any sensible measure, you could choose the Sahara Desert as almost all sand, right? And that's a situation that is generally true for typicality statements. For instance, typicality statement now in mathematics would be a typical real number is irrational. And you can ask, well, what do you mean by what measure? In this case, technically, we don't need any measure at all. We could say, well, the rational numbers are a countable subset of an uncountable set. But to speak about measures, it might be natural to put the uniform measure, let's say on the unit interval, and then say, well, the rational points are a set of measure 0. But maybe this uniform measure is somehow suspect as it reeks too much of a principle of indifference. So fair enough, then change the measure like this, or put a sort of Gaussian measure, or tilt it to the left or tilt it to the right, or take a discontinuous measure. In this case, it really doesn't matter. Any reasonable measure, in this case, the precise statement would be any measure that is absolutely continuous with respect to the Lebesgue measure, agrees on the fact that the rational numbers are a set of measure 0. Right? Just don't be too extreme. Right? Don't put like a delta distribution on a rational number and call this your typicality measure. Of course, mathematically, it would then be true that according to this measure, let's say almost all real numbers are 1/3, right? If you put a delta measure on 1/3, but aside from this technical lingo, it would obviously be an abuse of language. This measure does not, such a measure does not express our intuitive understanding of what we mean by almost all but almost all rational numbers. And of course, in physics, the situation is not quite as nice because typicality and atypicality statements don't refer in general to sets of measures exactly 1 or 0, but only nearly so. And this puts a bit more constraints on what kind of measures can be considered equivalent as typicality measures. But in general, it's true that relative to a measure, really you would have really radical deviations from that measure would be necessary to come to different conclusions about which sets are very small or very large. The other answer, that is actually the one Boltzmann has also given, which is immediately after this quote that I showed before. He says the criterion of equal possibility or equal probability of different state distributions is thereby always given by Liouville's theorem. So Liouville's theorem, here speaking about classical statistical mechanics, of course, the theorem that the uniform measure, the Lebesgue measure in canonical coordinates on the phase space of the theory is a stationary measure, is preserved by the dynamics. So if you have here a certain region of phase space A, and it evolves, here this phi is the Hamiltonian flow, so it evolves by the microscopic dynamics, then the measure of A will be the same as the measure of this time evolved set. And I think it's also clear why you wouldn't want typicality statements to be somehow time dependent. Why a set of initial conditions that you deem very large should be judged very large by the same standard if you do it tomorrow or in a week or in a year. Another perspective that I find useful to explain why we would want a stationary measure is that ultimately we don't want to quantify initial conditions, but we want to quantify possible microhistories of the universe, right? Initial conditions, so-called initial conditions, are really just a means to parameterize possible solution trajectories. And a stationary measure, here I skipped over the natural generalization, for instance, in quantum mechanics, where we have, time-dependent dynamics given by, in terms of the wave function. Natural generalization would be equivariance, right? Stationarity or equivariance just ensures that that a measure on phase space can be lifted canonically to a measure on possible solution trajectories, no matter which time slice you use to parameterize them. So I think this is another way to see why stationarity is a very natural desideratum for a typicality measure. But that might be a point actually where Barry and I disagree with. So the Mentaculus often have this, usually has this view that there is really a physically distinguished initial time, maybe the Big Bang, to which statistical arguments or probabilistic reasoning can refer. And it's okay that this one time is somehow distinguished for the purposes of typicality reasoning or probabilistic reasoning. So this might be a point that we disagree with. But in the end, so in Bohmian mechanics, the situation is actually very nice, because as Ward and Shelley proved, this chi-square measure is actually the unique equivariant measure under certain condition, like the unique equivariant measure that depends only locally on the wave function and its derivative. Right? In classical mechanics, there are still many different stationary measures. For instance, every density which is a function of the Hamiltonian would be a stationary measure. So this criterion of stationarity doesn't give us a unique measure and may not even rule out evidently inadequate choices, such as really a delta measure concentrated on a stationary point of the dynamics would technically also be a stationary measure, right? Like a point that is a fixed point of the dynamics. So in general, the situation might not be as nice as in Bohmian mechanics, and we do have to appeal to weaker criteria, right? Like naturalness, simplicity, or just intuitiveness that that the measure is really intuitively compelling in expressing what we could mean by very large or very small sets of initial conditions. Now, there's another technical assumption which I didn't mention, which both the Liouville measure and the Bohmian typicality measure satisfy, which is invariance under the fundamental symmetries of the theory. That's another nice desideratum that I won't discuss in detail. But still, the point remains that in the end, we might have to fall back on arguing that certain measures are reasonable choices of typicality measures. And I'm fine with that. But Barry asked more philosophically a different question, if I can paraphrase. So what is this really in nature that makes a certain choice of typicality measure true? Right? And according to what you call the typicatulus, right, a certain typicality measure would be a Humean law. So it supervenes as the best systematization of contingent regularities in the world, which just means that the dynamical laws plus a certain typicality measure plus the past hypothesis, they provide the best systematization of the world. Right? So in this sense, the world is the truth maker of a certain choice of typicality measure if the best system account is really successful. So if you find it plausible that in the end of the day, there's an objectively best system that that assigns lawhood to a certain set of theoretical postulates. So under my view, well, let me stop here and say that, yeah, this is a viable compromise, so to speak. Not one I would endorse, but it is a viable compromise. And now I could say that I could pretend to be Humean and argue that why, even if I were Humean, I would not like to understand the typicality measure as a Humean law. But indeed, I think it's fair to say that Barry is right. The main disagreement here is really about the nature of laws, first and foremost, and just the status of the typicality measure second. Because I am an anti-Humean, I believe that laws exist in a metaphysically robust sense, right? Something that really guides or constrains the possible history of the universe in a modal, metaphysically robust sense. And one issue then is that simply that I don't really see this option of including a typicality measure among non-Humean laws. Like sometimes Humean claims that I wouldn't even have the option of including the past hypothesis among the laws. I don't think it's true. Shelley and Eddie Chen actually have a nice paper about that, because the past hypothesis does generally constrain nomic possibilities, and you can interpret it as a non-Humean law, but it's a typicality measure doesn't really constrain nomic possibilities. So it's not clear if it's a so I don't think it's not the non-Humean has the option of really including it as a law of nature. The other point that I think is also a problem for a Humean, but in particular for an anti-Humean, is that I believe there are true dynamical laws in nature. And I really hope we'll be able to find out what they are. But as I said from the very beginning, that was the problem that sort of started this whole conversation. Special initial conditions, right, could lead to virtually any phenomena we like, right? So tweaking the so-called typicality measure in the right way could make virtually any possible phenomena typical. Right, so I don't think that epistemically the dynamical laws and the typicality measure have the same status. The typicality measure, the notion of typicality, must be more robust, right? Because some notion of typicality must be not part of the law hypothesis, but part of the backdrop against which we evaluate possible law hypotheses. Right, and I think that's true in practice. As long as you work in, let's say, in the framework of classical mechanics, and you have a certain model that doesn't fit the phenomena, right? The first thing you would do is adjust the Hamiltonian, so adjust the dynamical laws, not play around with the typicality measure. So you can say that, well, according to the same dynamical laws, the observed phenomena really come out as typical. That's not something we would usually do. And so in some sense, the typicality measure, or some notion of typicality, must be more robust epistemically, less empirical, so to speak, to allow us to judge dynamical hypotheses in the first place. So according to my view, ultimately the choice of typicality measure can be reasonable or justified, but not strictly speaking true. And yeah, that empirical adequacy, right, that a certain typicality measure together with the laws just fits the phenomena, can be part of the justification, but not the main thing, for reasons that I just explained, right? If we could tweak the typicality measure as much as we wanted, we basically couldn't falsify the dynamical postulates anymore, because we could make virtually all phenomena come out, quote unquote, typical. So in my view, the typicality measure is not a law, but rather pertains to a way of reasoning about the laws. And this is something that Humeans in particular usually find somewhat vague or mysterious or suspicious. So to end with, let me try to couch this in a way that might make it more plausible for Humeans. Okay, so according to Humeans, the laws of nature are supposed to be the axioms of the deductive system that strikes the optimal balance between simplicity and informativeness in describing regularities in the world. Right? Now I say, well, okay, fair enough. So a necessary criterion for informativeness is that the theory makes the relevant macro-regularities of our world typical. Right? And then you ask, okay, typical with respect to what measure, right? But this is very similar as asking, well, a theory is simple with respect to what measure. And I'm not trying here to make a so-called like two-quokka argument, like, well, okay, I'm vague about the typicality measure, but you're also vague about what you mean by simplicity. No, I mean, that's exactly right, that simplicity, if we talk about simplicity in this Humean sense, it has a normative character, right? It pertains to giving reasons for accepting or rejecting a particular theory, right? And of course, the measure of simplicity could not itself supervene as part of the Humean best system, because otherwise, if every best system candidate could postulate its own measure of simplicity, we couldn't use the criterion of simplicity to adjudicate which system is best to begin with. Right? And also, while some people might try to put down exact axioms that that define what we would mean by simplicity, this would seem for me to go in a wrong direction, because simplicity has this kind of normative character, and because it's not clear why any set of axioms ultimately should be more compelling than our informed judgment about which theory is more or less simple. And typicality is actually much less vague than this notion of simplicity, but my point is that it has also, in part, this normative character, right? Together with this rationality principle that I attributed to Tim and mentioned twice before, right? Typicality has figures in this context of justification, of giving reasons for accepting or rejecting a particular theory, right? A reason for accepting it being that it explains relevant regularities by making them typical, rejecting by making salient regularities that we observe, rejecting because it makes certain regularities that we observe atypical. So again, I'm not trying to say, well, I'm vague about the status of typicality, you're vague about the status of simplicity. I think it is exactly right that both of them have this kind of normative character. Typicality, at least in part, right? So in part, it figures in this context of justification, of giving reasons for accepting and rejecting theories. And this is why it's not and cannot be a completely empirical postulate, and why it may also ultimately, to some extent, really resist a complete rigorous axiomatization of sorts. Okay, that's it for now. Thank you very much.
Thank you, Dustin, for this very nice talk. Okay, so let's open it up for questions. We are already, yeah, it's already 6:30. So I'd say we have some few questions on the talk and then open it up for the general discussion immediately. So Barry, first question. You have to unmute yourself. We don't hear you.
Okay, so thanks, Dustin. That was great and really interesting. I just wanted, there's a lot to talk about, but just one small point about Cournot's principle.
Mm-hmm.
So you seem to be saying that there's no testing a probabilistic theory without Cournot's principle. But I don't see that that's so. I mean, there's Bayesians don't appeal to Cournot's principle.
Not explicit.
And likelihood, and you know, if you're doing likelihood testing, you don't appeal to Cournot's principle.
Not explicitly, but ultimately, I don't know if you take a Bayesian view on hypothesis testing. Isn't the criterion for like rejecting the null hypothesis that you end up with very
Bayesians
low
don't reject.
hypothesis?
Bayesians don't reject or accept. They change their prior degrees of belief to posterior degrees of belief.
Yes, but then if you want to reject the null hypothesis, so accept, for instance, that the COVID
Well, that's an
vaccine,
action. So rejecting the null hypothesis might be writing a paper that says, you know, that's no good. But then you're doing an action and you use decision theory. what are the utilities of writing a paper which says, phooey to some hypothesis? But as far as belief is concerned, it's not, you don't accept or reject. So you don't using Cournot's principle, and when performing an action, you're not using Cournot's principle either.
Well, but then you're using let's say a pragmatic version of Cournot's principle, like a version like if your credence in something is very close to zero, you should act as if that event will not happen. Depends what the utilities are. Ah, okay, I see what you're saying. Yeah. Yes, I see what you're saying. The thing is, I think that in general, at some point, and maybe that might be a genuine disagreement between the Bayesians, one of many genuine disagreements between Bayesians and like advocates of Cournot's principle, that at some point you neglect possible but atypical events just based on their extremely low probability alone, even if those events can have catastrophic implications, right? Because otherwise you would just end up being a paranoic who just worries about the most unlikely highest impact events possible. So always making a sort of Pascalian wager of sorts. So I think at least then at those points when you, I don't know, neglect the possibility that the quantum vacuum may decay tomorrow and the entire universe is annihilated, then at least at this point, you're really applying Cournot's principle and neglect the possibility of an event just based on its extremely low probability alone.
Well, my utilities are involved even in that one. Okay, and the probability is just so tiny that, and anyway, there's nothing I could do about it anyhow.
Okay, that's good.
Okay, but I do think what comes up here, which is really interesting for the whole discussion, is that there's a big package of views that are related to each other. Bayesianism, probability, Humeanism, the principle on the one hand, typicality, Cournot's principle, and anti-Humeanism. So on the other hand, they don't necessitate each other's in the package, but they're close together, and it's interesting to see the two big packages developed.
Yeah, definitely. I think I think there are at least logically viable options to pick and choose, like be Humean but endorse the typicality.
Yes, you showed
Cournot's principle. No, but in principle, but basically, you're right, and I mean that's something that I always admire about your work. That you're always looking for these connections of things of different philosophical positions about different issues that nonetheless tend to come in these packages. So there are certain interconnections between them for sure.
Thanks.
Okay, so thank you. I think there was another question by Sylvia. You were next.
Okay, thank you. Yeah, thank you very much. It was a very clear and didactic talk. So I'm still organizing my thoughts a bit, but there was at least one thing now, just with the discussion previously with Barry, I was thinking whether it would make sense to sort of broaden up Cournot's principle towards the Lockean thesis, which is from a slightly different context, the idea that if a probability is high enough for practical purposes, so there are some utilities in the background, sometimes you can believe something as if it was true, even though you know you have a probabilistic theory for it and it's not exactly certain. So that was one thing I was just thinking now during the discussion. But I actually raised my hand to clarify something else. So when I read up on typicality, and I think it was an article or a chapter by Shelley Goldstein, I read the explanation about hypothetical ensembles as sort of a health warning, like be clear that we are talking about hypothetical ensembles. That doesn't mean anything corresponds with it. In reality, it doesn't imply a real ensemble. But in your talk, I had the impression that you used it slightly differently, though related. I had the impression that you were saying, and correct me if I'm wrong, that as long as it's about hypothetical ensembles, then it's typicality. And if there are real ensembles or actual repetitions of trials involved, then that's a reason to think of probability. Did I understand that part correctly, or did I miss something there? I took that from your example with ideal gas molecules, that there were real, there are really many molecules, but then there is also a hypothetical ensemble involved in the derivation. So did I read that correctly, that that is why you stick to typicality in that case when it's only hypothetical, or did I simply make up a story that was not there?
Okay, so to answer the second question first, there was not per se a theoretical ensemble, but there was, in the example, there was the actual empirical distribution of velocities in the gas, and then there was, so to speak, a theoretical empirical distribution, which is the Maxwellian distribution. And then the statement is that typically, meaning for a set of microstates that is whose measure is very close to 1, the empirical distribution will be close to this theoretical distribution, which is the Maxwellian distribution. Now, I'm not sure exactly what point the paper was making that you were reading, but of course, one important remark is that as long as you're dealing with a finite number of degrees of freedom, right, these theoretical distributions will just be an approximation to the typical, these theoretical distributions will just be an approximation to the typical empirical distributions, right? So also something that Boltzmann said, that they will just be approximately Maxwellian distributed, not exactly. But often, of course, it's just convenient to talk about, sharp probabilities and sharp distributions. Sure. And that might be the point where you say, okay, that's really an idealization that would only be typical for infinite ensembles.
Sure.
To the first part of the question, I'm not sure if you're asking because you know the work, but there exists this book and papers by Hannes Leitgeb that go very much, I think, in the direction that you mentioned. It's called the stability theory of belief. And he doesn't talk about typicality or Cournot's principle, but he talks about the Lockean thesis and reducing degrees of belief to belief simpliciter. So at what point, what circumstances is it rational to say if my degree of belief in a certain proposition is above a certain threshold, then this proposition is believed simpliciter. That goes very much in this direction. And I actually used some of his arguments to talk about typicality and Cournot's principle, even though this is not exactly what his work is referring to, but it goes very much, I think, in the direction you might have in mind.
So the connection is there. I didn't just imagine that you were inspired by that. Okay. Thank you.
I understand, yeah.
Okay, thanks. So the next question is by Tim.
Yeah, I don't really have a question. I just had a very short comment with respect to Barry's point about packages, right? That if you're dealing in probabilities, it's a natural thing to then try to quantify credences by real numbers, and then in practical decision making to calculate expected utilities, and then choose the action with the highest expected utility. So that's a kind of package of how all those concepts fit together. I just want to mention, and I think he's right, you have to deal with the totality of things. I think, it's worth noting that that particular package really screws up the practical decision-making theory badly with St. Petersburg cases. And that there is a way to do the whole thing over again with typicality. to redo also the practical decision making, also the epistemology, using basically typicality resources and resources less detailed than using real numbers. And for anybody interested, I have a paper on this called Credence and Chance Without Numbers, and with the Archimedean property, which is on the PIT website. So I mean, it's to agree that there's all of this gets embedded. Obviously, that probability talk has become embedded throughout a big swath of philosophy. And if you want to say, let's think in terms of typicality, you should try and rethink that whole swath. But I think you can do it, at least to an extent. And furthermore, the usual way of doing it has real problems, which have never, to my mind, been properly addressed.
Yeah, that's a really good point. So just for those, if there's someone who doesn't know this, some Petersburg cases are example where, let's say the expectation value can go to infinity, while the risk of ruin, like the risk of going literally bankrupt, can go to 1, right? So that's like those are these cases with very high expected utility, but where you typically lose everything. And then I think most people agree that you should follow the typicality reasoning and not take those kind of St. Petersburg bets.
Okay, so let's move on. The next question has been by Lev, or comment.
My first comment, I was surprised by your 3 examples. Mm-hmm. Because later you said that we can, by playing with initial condition, to do everything, and they were supposed to, but I don't see how you can make stones moving on hyperbola instead of parabola. It has nothing to do with initial condition. If stones remain stone, then physics tells you they will go on parabola. And your example with a fair coin, this is the definition of a fair coin. I'm not sure what you exactly mean. Maybe the coin from your pocket. Then it might make some statement. The fair coin make half. This is, I think, it's a definition. And also, I don't see how the apple jumps from the surface. You need very, because I don't think physically. Even I have all kind of initial condition of Earth. Very extremely special how it can kick, because I cannot even arrange mechanically. Usually, it will not jump properly. It will be just ruined. It will not jump as an apple. So all your examples were kind of strange for me. Okay. And then maybe two more kind of more general comments. Typicality, the definition was that it's almost everything is of this type, if not all. Mm-hmm. So, and then you say there is a difference from probability, but usually what we do in probability, at least in physics, statistical mechanics, physics, we just say, let's look on all, we put some discretization, put all cases and count. And if the vast majority is of particular type, then we say that this is probable. So what is the difference between probability and typicality? And the last maybe comment or question for general public is, there are many in most textbooks on quantum mechanics. In the beginning, there are some kind of questions and puzzles, how it can be understood. There are some philosophical issues about foundations of quantum mechanics. If I read books on thermodynamics, maybe I haven't read too many, I don't remember such things. They all say that if you take statistical physics, then you get thermodynamics without problem. History, Boltzmann, Carnot, whatever, this is history. Today, I don't see there are any kind of real difficulties for physicists to get thermodynamics out of statistical physics. So I don't, why, and it seems to me that the weight of analysis of Boltzmann, Carnot, typicality, and whatever is similar to the discussion of foundations of quantum mechanics, where I think physicists see a real problem, and I don't think that they see real problems in the basis of thermodynamics. Sorry, maybe too many questions.
Yeah, I'll try to address them if I remember them all. So first of all, with my initial examples of macroscopic regularities, I mean, I think the case of the apple is easy, just because if you have time reversible symmetric laws, the reverse process is possible. So usually the apple falls to the ground, gives off as kinetic energy, as heat energy to the ground, but in principle, the reverse process is possible also with all the particles in the ground moving in just the right way to push the apple back up in the air. So I think that example is clear that actually apples spontaneously jumping up from the ground to the tree is not impossible. It's just atypical. Concerning the example of the stone throw, well, I can't give you now exact initial conditions for which the stone would fly on a hyperbolic trajectory, but I think the quote from David Albert says it very well, right? Nothing in the mechanical laws would prohibit the stone from ejecting one of its microscopic constituents with extremely high momentum in one direction while the stone is careening off in the other direction. Of course, if you have conservation of momentum and stuff, the mathematical center, no, that's not true. No, that's not true. Sorry, forget the last part. But I mean, that's obviously an example that I think is possible. That I think it's physically possible and would lead, but atypical, and would lead to a completely different kind of macro behavior. And that's actually, I think, an important point, that if one really appreciates the fact that macroscopic bodies are really composed of a great number of microscopic constituents, even the apparently deterministic predictions that we make by treating, let's say, Newtonian systems as initial value problems are ultimately typicality statements. So we are ultimately assuming a typical evolution. The first point, yeah, that's well taken. It does sound or can sound circular or tautological if I say that. If I say the frequencies, the outcome frequencies of a fair coin are 1/2 and 1/2, I should say just a balanced coin, a coin that is physically symmetric. Right? It doesn't have any, like a symmetric mass distribution. Then the last point, well, I agree that most of the questions we have debated here today are not of practical significance for a working physicist. That's also part of what I said at the very beginning, and I think Barry and I agree on maybe everything that is really relevant to the day-to-day work of a physicist, and a lot of it being Boltzmann. So actually many physicists do not appreciate or agree with the Boltzmannian framework and the overall reasoning, but I mean, to the degree that they do, the things that Barry and I disagree about, they have really practical consequences for the physicist. But I think that this debate and this discussion, in particular the notion of typicality, does have really a great significance for debates about foundations of quantum mechanics. I mentioned the justification of the Born rule in Bohmian mechanics, which is based on a typicality argument. And had I known that you were here, I could have actually put up quotes by Hugh Everett, because Hugh Everett was maybe one of the first to use very explicitly this notion of typicality to try to justify the Born rule in the many worlds theory. So he said, you know, he was asking about what kind of statistical regularities would a typical observer in this multiverse C. And I think that one of the main reasons that most modern Everettians, including you, I gather, don't reject Hugh Everett's initial account of the Born rule in Everettian quantum mechanics is really that they don't understand or don't agree with this concept of typicality and typicality arguments in general. If there was a third question and I forgot.
Oh, no. The third question was, okay, no, I think yes. It was the second question, that if you assume that all states are equally probable, and then you count your states in discrete systems, then it seems in typicality and probability, it's the same story. So why people introduce this word of typicality when it just the assumption that all initial conditions are equally probable, which in some cases one can have justification for this, and then we don't need too many concepts. I'm kind of surprised that there are so many words: credence, propensity, typicality, probability. Clear probability, it's difficult concept, but I don't think there are any kind of, I still hardly see the differences between all these things.
It's true that I think if we discretize, then we would all agree that somehow the appropriate measure for either probability reasoning or typicality reasoning would just be the counting measure, right? But I think in this case, I would say the typicality reading is even more explicit. That counting is just about saying, what is true for the great majority of possible states or initial states of the system. If you want to say, well, I discretize, and then by counting, I'm making a probabilistic assumption that every one of these states is equally likely, then of course there are additional issues about, well, what do you mean by that, and what justifies this probabilistic assumption? So then I think in those cases in particular, the typicality reading is more compelling than any sort of probabilistic reading.
But my problem, what is the difference? I agree that there is this question to justify why all initial states are equally probable. It's a maybe deep question in some situation. But I don't see the difference between this statement and typicality. You say typicality is better. It's the same statement essentially.
No, I think it's better because the question that you agree arises when you speak about probability, I think doesn't arise if you speak about typicality, in particular in such discrete cases where we can just count and can say that certain statistical regularities or certain regularities in general obtain for nearly all possible states or nearly all possible initial conditions, and we just mean, well, for 9,998 out of 10,000 or whatever, then I don't think there's anything else to justify or even any meaning to the assumption that, well, any one of these states is equally likely and so on. So I think that these questions or these problems that you see yourself just wouldn't arise if you think about it in terms of typicality, right? But I agree again that most of these debates are, well, I would say they are actually similar to debates about quantum foundations, where for all practical purposes, people agree on how to work with a formalism and make predictions, but then there are, deeper question about what it all really means and what it is all really saying about the world.
Okay, thank you.
Thank you.
Yeah, as we are already over time, I think this is a good point now to stop. Unfortunately, we have to stop the discussion, although I think there's still much more to discuss. But okay, so thank you both speakers again at this point. I don't know where Barry is, but here it is.
Okay. And yeah, thanks to you again for the discussion. Oh, and I just saw in the chat that Siddha noted I had a typo on my slides. I guess it's just because sometimes I work with normalized and not normalized empirical distributions. So if probability is P and you repeat the n trials, then P times n, approximately P times n, it would occur, not P divided by n, or what I had.
So that was the test for the people if they follow the talk.
Right.
Exactly.
But thanks, Siddha, and thanks again for the invitation, for the great questions and interesting discussions.
Yeah, thanks to the audience. And let me hand over to Dirk. He wanted to announce the next session.
Just traditionally the final word again. It was really great having you here. Also that we had a nice focus on philosophy, makes the whole Laws of Nature series a bit more colorful. And yeah, thank you very much for that. Next month in February, we're going to have a talk on the causal fermion systems, which is an alternative formulation of quantum field theory, and I think has also a lot to discuss about, by Felix Finster from the University of Regensburg. And I would of course be happy if some of you would also show up and we'll have also a vivid discussion like this. So long, I would say, take care, stay healthy, and see you very soon.
Thanks.
All
Thank
right.
you.
Goodbye.
Thanks. See you.
Thanks and bye.
Bye-bye.
Bye.
Bye.